So, we were discussing the power series sigma a n z minus z naught to the power n is 0 to infinity. That was the power series, and we have seen that this power series convergence behavior of the power series depends on the coefficients. So, for variable z, z is variable. Once you fix up the z, then it becomes a power series, okay, where all the results, ratio test, comparison test can be applied over this. So, if you use those application, then we have seen that the power series, there are power series which converges only at a singleton point, that is z naught itself, or it will converge throughout the entire domain, or there are some series which converges inside a disk and diverges outside. So, basically the behavior of the convergence behavior of the power series, that is interstate, and particularly those power series which behaves like then inside some disk it is converges and outside it diverges. So, we can identify a circle of the convergence, so that all the points inside the circle we can say the series converges, and the point which is outside of this diverges. And this follows from the previous result which we have already discussed, that if a series, if this series with central z naught and converges at a point z1, then it will converge at every point inside this z1, and if it diverges at the point z2, then it will converge, it will diverge outside of this. So, this is the, here it will this is the point for diverging, where the this is the point for convergence, where the series converges. Then what we have seen is that all the points at inside this the series will converge, while the point outside of this it will diverge. Now, if slowly if we keep on increasing the point, this one point here, here and there, and reducing here, then you will get one circle, and that circle you can identify the circle, so that when you take this circle mod z minus z naught, say radius r, if I take, then we can say that the set of all points, okay, the set of all points inside the circle mod z minus z naught less than r, the series is convergent. Series converges, the power series 1, power series 1 converges over the set of all points inside this circle, and suppose and diverges for all point over the set all points where mod z minus z naught is greater than r. Okay. Then this mod z minus z naught equal to r, this is known as the circle of convergence. Okay, and r is called the radius of convergence. Radius of convergence. Okay, that is what we are interested. Okay. Now, that we have seen that if r is the radius of the convergence, then all the points inside the region mod z minus z naught less than r, the series will be convergent, and the point outside of this region z minus z naught greater than r, those points will lie in this region, will diverge. What about the point on the boundary, on the circumference? So, nothing can be said, not a, we can say no general statement statements can be made about the convergence of a power series convergence of the power series 1 of power series 1 convergence of the power series on the circumference of the on the circle of the convergence. Instead of circumference, let us write circle of convergence. It means the behavior of the power series over the circle of convergence varies. There are the power series which may not converge at any point inside over this circle of convergence. There are the series where it converges at every point on the circumference convergence, or maybe a series which converges only at few points and nowhere else. So, let us see the behavior of the convergence of the power series or behavior of the power series on the circle of convergence of power series on the circle of convergence mod z minus. So, behavior of the power series on circle of convergence. So, let us take the few examples. Suppose I take the example here, let r becomes 1, let us choose r equal to 1 and z naught equal to say 0. So, with center 0 and radius 1. So, let us draw the consider the power series sigma z to the power n over n square. N is from of course 1 to infinity, because otherwise it is not defined, 1 to infinity. Now, obviously, this series is convergent, in fact absolutely convergent inside the circle mod z less than 1, because and diverges for mod z greater than 1. The reason is because if you use the ratio test, then what is the ratio test says that un plus 1 over un, that is n plus 1 by n whole square into z mod z. This is the un plus 1 over un. This limit as n tends to infinity is mod z. This is the ratio test. Say un plus 1 over un. Un stands for unz stands for this function, where the unz is z to the power n over n square. This is our unz z square. Okay. So, if you apply the ratio test, then you are getting limiting value to be this. Now, if this is less than 1, clearly if mod z less than 1, series converges, greater than 1, series diverges, and equal to 1, test fails. Okay. So, let us see that series where it can. So, suppose I choose z equal to e to the power I theta. Okay. Now, e to the power I theta, where the theta lying between 0 and 2 pi, one side is okay, 2 pi. So, it is a point lying on the circumference of the circle, centered at 0 with the radius 1. These are all points we cover. So, what will be our un? The un becomes unz, this becomes z, means e to the power n I theta by n square. Okay. Now, this mode of this thing is dominated by 1 by n square, and 1 by n square sigma is finite, since sigma 1 by n square 1 to infinity is a convergent series. So, this is each term of the this series is dominated by a non-negative real numbers, where the series is convergent. So, by comparison test, we can say that the series this z to the power n over n square 1 to infinity converges absolutely for all z lying on the circumference mod z equal to 1, or satisfying the condition this. It means this series converges everywhere on the circle of convergence. So, those are series converges everywhere absolutely everywhere on the circle of convergence. That is mod z equal to 1. Okay. So, this will be now, let us take another example. This is the example 1. Let us take the other examples 2. Choose the z to the power n by n 1 to infinity. Now, if you look this way, then obviously, this series converges for all z mod less than 1, diverges for all z which satisfying this condition mod z greater than 1, and for 1 when z is equal to 1, it is harmonic series, so diverges, while z equal to minus 1, it is alternating series. So, by Leibniz test, the series converges. So, what we can say here, that it converges at minus 1, but diverges at 1. It means the points where it converges and diverges. Okay. Then third case is 1 and minus 1, it converges and diverges. Okay. Similarly, I and minus I also you can establish the similar things for it. Okay. So, diverge. Now, if we look the sigma z to the power n 1 to infinity or 0 to infinity, then it diverges everywhere. Why? Because what is the coefficient a n? A n is 1, and that does not go to 0 as n tends to infinity. And in fact, what will happen is non-zero term, and there is one term if the sigma u n z to the power n is there, and if all the terms are negative and this does not go to 0, any term must go to 0. So, here the z n is 1 of course. So, when you take the mod n, or you can choose the like this, say z equal to 1, it will diverge, z equal to minus whatever may be mod z, it will always be 1. Okay. So, it will diverge everywhere in the complex plane, okay, because this follows from the real. A series whose nth term must go to 0, but nth term will not go to 0 because it is okay. So, it diverges. So, what we see here, there is a series whose convergence on the circumference is granted everywhere. There are series which converge only at few points, but nowhere else, and the series which converges nowhere convergent. So, the behavior of the series power series on the circle of convergence is not definitely, cannot be definitely said. It depends on the series. Okay. So, this is one. We cannot say anything about comment. Now, as we have seen that this convergence and the divergence of the series totally depends on the coefficients. So, why do not we have a results or formulae which depends only on the coefficients and but capable of identifying the given series to be convergent or divergent. Okay. So, that will also give the formula for the radius of convergence, so that you can find the region of the convergence where the series converges and the other region where it diverges. Okay. So, let us see the result, which is in the form of the theorem. The result is about the radius of convergence, and we denote this by R. Okay. Suppose that sequence n converges with the limit. Okay. Let sigma n say z minus z naught to the power n is 0 to infinity, we are given power series. Power series in z minus z naught, in z minus in the power of z minus z naught with centered z naught. Okay. And let us suppose, let limit of this, limit of mod n plus 1 over n as n tends to infinity is, suppose this limit exists, and suppose L star exists, and say it is L star. Okay. That is with it. Now, if the result is, so what it says is that if L star is 0, if L star is 0, then the radius of convergence R will be infinity. Okay. And the power series converges. So, the power series converges at every point for all z in a complex plane. See, if L star is not 0, if L star is not 0, then we can define the radius of, then the radius of convergence R is nothing but 1 by L star, and that is equal to limit of this as n tends to infinity mod of a n over a n plus 1. That is. Now, if third case, if our if mod of a n plus 1 over a n, if mod of a n plus a n tends to infinity, then the radius of convergence R will be 0. That is, converges only at the center. That is, power series converges only at the center z naught. So, this is the result, and this result is given by Cauchy-Hadamard. So, it is also known as the Cauchy-Hadamard theorem, Cauchy-Hadamard formula, or you can say Cauchy-Hadamard formula. This is also known as Cauchy-Hadamard formula. Okay. Let us see the proof of this. Proof is simple. What is given is, given the power series sigma a n z minus z naught to the power n 0 to infinity with central z naught in the power of z minus z. Now, use the ratio test. So, if you take the ratio test, u n plus 1 over u n, that is a n plus 1 z minus z naught to the power n plus 1 over a n z minus z naught to the power n, this u n, this is equal to what? Mod of a n plus 1 over a n into mod z minus z naught, but it is given the limit of this exists. So, if we take the limit of this as n tends to infinity, this is equivalent to the limit of this as n tends to infinity. Mod z minus z naught is free from n. So, basically it is equal to L star mod z minus z naught. Okay. Now, if L star is 0, is it not? If L star is 0, case 1, if L star is 0, it means this ratio test is strictly less than 1. So, by ratio test, the series, the power series converges everywhere, is it not? So, less than 1. So, this series converges everywhere in the complex plane. Complex plane, that is the radius of convergence R, radius of convergence will be equal to infinity. R becomes infinity because it converges everywhere in the complex plane. Okay. And if L star is not 0, then let us write it, this is suppose L, then let L is equal to L star mod z minus z naught. Okay. Now, if this is two cases, either this will be less than 1 or greater than 1. So, if it is less than 1, then convergent, if it is greater than 1, then diverging. Okay. So, then it implies then greater than 1 divergent, that is mod z minus z naught, mod z minus z naught, this is strictly less than 1 by L star, then the power series converges. And if it is greater than 1 by L star, if it is greater than 1 by L star, then the series diverges. Series diverges. Okay. So, this convergence. So, it means if I take it 1 by L, choose 1 by L star as R, radius of convergence. So, this is the circle of convergence, that is with radius R. So, circle of convergence with radius R means mod z minus z naught equal to R. And then what we are getting is that if R becomes 1 by L star. Okay. So, L is 1 by R, that is formula is this, is it not? L star is what this. So, from here we get 1 by R is equal to L star, that is equal to limit as n tends to infinity mod n plus 1 over mod n, where R is the radius of convergence. So, this shows it. Okay. So, this proves that convergence. So, series converges inside them. Now, what happens if the L star does not exist, it goes to infinity. If it L star goes to infinity, is infinity, then R becomes 0. So, in that case the series is converging only at the center, that is all. So, that is the this greater than or sufficiently large. So, implies series diverges for all L star is infinity, is it not? So, what do you mean by this will be L star is infinity, this part L star is this. Okay. So, this is infinity. So, we are getting what mod of z minus z naught, this is basically the terms are greater than 1, is it not, both mod of n plus 1. So, this shows that mod of n plus 1 is greater than mod of n, is it not? The terms of keep on increasing. So, the series diverges at every point. So, R is 0 means the series diverges at all points except 0, except z naught, that is all. There is no point, ratio test. Okay. Implies divergence, because this entire thing is greater than 1. If it is greater than 1, then we get this divergence. Okay. So, L star clear. So, this shows that. Now, take some example, then it is okay. Let us take it. Suppose I take this series, find the radius of convergence of this series say sigma minus 1 to the power n z n over say minus 1 to the power n z n maybe z minus z cube. So, 0 to infinity 1 minus z square. Okay. So, this will be the equal to factorial n, or minus 1 you outside 1 minus, or let it be without 1. Okay. Let us take this only. Suppose I take this series. Okay. Then what happen is mod n plus 1 over n. This is equal to what? Mod n plus 1 is factorial n plus 1 mod of this, and limit of this as n tends to infinity is the same as limit of this as n tends to infinity, which is nothing but what? 0. So, our L star is 0. L star is 0 means R becomes 1. So, this is our L star. So, series converges everywhere. Okay, like this. Similarly, we can go for others. Now, if you take a some point, suppose another example, if I choose, say discuss the power radius of convergence of find the radius of convergence of the power series sigma factorial 2n over factorial n square z minus 3i to the power n is 0 to infinity. Suppose I take this. Okay. Now, here this is a power series centered at center is 3i. Okay, 3i. So, let us find out the first radius of convergence. So, what is our n? N becomes factorial 2n over factorial n square. So, n plus 1 is factorial 2 n plus 1 over factorial n plus 1 whole square. So, n plus 1 over n or n over n plus 1 the radius of convergence limit of this as n tends to infinity. So, what will the radius of convergence is n over n plus, if I complete it, then this comes out to be what? And basically just you find a 1 by 4. Okay. Limit will come out to be 1 by 4 using the factorial values and other. It means that is radius of convergence R is 4. So, the series converges inside the mod z minus 3i less than R 4, and that will be the this is 1 by 4, sorry, this is 1 by R, this is R. So, radius of convergence is 1 by 4. So, 1 by. Okay. So, this will be the answer. So, this way we can go. Now, in case if the limit does not exist, then we will choose the next limit superior of this. Note, if the limit of this mod n over n plus 1 as n tends to infinity, if this limit does not exist, okay, then you find out the limit superior, then choose limit superior of this. Okay. So, if that is n plus 1 over n, if limit does not exist, then choose the upper part of it, okay, like this. Then choose the limit superior. Similarly, for other case, same results is another result is for the ratio test, nth root test. The radius of convergence R having the formula 1 by alpha is limit mod n to the power 1 by n as n tends to infinity, or if limit exists, or limit superior as n tends to infinity mod n to the power 1 if limit does not exist, but finite values, means it should not be infinity. Okay, otherwise mean various limits are okay. So, here this is the power series, sigma a n z minus z naught to the power n 0 to infinity has radius of convergence r, where 1 by r is given by this formula, has radius of convergence r, where 1 by r is given this one. Okay. So, this will be. So, for example, if we take this function, if it's series, find the radius of convergence of the series of the power series sigma 1 plus minus 1 to the power n plus 1 by 2 to the power n, then z to the power n, and this 0 to infinity. Now, if we look the series, what are the n's? N are 1 plus minus 1 to the power n plus 1 by 2 n. If we look this say, then mod n to the power 1 by n, it does not go to, because this limit will tends to always half. So, clearly for odd, when n is odd, then then mod of n to the power 1 by n, this will go to half when n is odd, because it becomes minus. So, this will be 0 and power half it. But when n is even, the limit will come out to be what? 2 plus 1 by 2 n power 1 by n, as n tends to infinity. So, it will go to 1. Okay. So, limit will be half and 2. So, what is the limit superior? Limit superior of mod n to the power 1 by n is 1. Therefore, radius of convergence will be 1 by r is the limit superior mod n to the power 1 by n, that is 1. So, r becomes 1. That is the answer. Okay. So, we can find out the corresponding. Now, next about we have a difference between the series of the real variable and series of the complex variable. The major difference is here. In case of the series of real variable, when the series converges, we have a function f x, okay, and the power series converges, we have a function f x which is continuous. We can find out the derivative of it, suppose, but after that we cannot say the further derivative is possible. But here in case of the function of complex variable, the power series, if it is convergent, it will represent a function f z, which is not only analytic in the region of the convergence, but is all its derivative will also be analytic. So, this will be justified in the following discussion. Okay. So, let us see the functions given by power series. Okay. Power series. So, this is what now when we have a power series sigma sorry z minus z naught to the power n 0 to infinity, let this power series has radius of convergence say r. It means inside the circle z minus z naught less than r, the series converges. Okay. So, once it converges, then for each z it will represent the some function. So, the sum of this series we denoted by f z. Okay. So, sum is denoted by f z, which is a function of z. It means, when we say f z equal to sigma n z to the power n. So, therefore, f z will be 0 to infinity z minus z naught to the power n for all z in the belongs to the region z minus z naught less than r. In this, thus it will represent it will convergent and represent a function f z. Now, what the result says is, the result is the function f z, the function f z given by 1, given by say 1 in the circle mod z, I am just saying mod z less than r, choosing z naught to be 0, particular case. Okay, choosing for simplicity. Okay, this is for simplicity, we can choose also given by 1 is less than r, or even z minus z naught also we can choose. Okay, so equivalently z naught is 0, fine, is less than r with r positive, with r positive is a continuous function at z equal to 0. It means the function f z sigma n z to the power n 0 to infinity given by 1 in z mod z less than bar is a continuous function in this. Okay. So, let us see how this prove. Once we prove the continuity, then all the things will come easily. Now, if we take z equal to the series is giving f z as sigma a n z to the power n 0 to infinity for z lying between mod z less than r. Okay. So, if we take z equal to 0, it means f of 0 is a 0. So, if I prove, required to prove is the limit of the function f z when z tends to 0 is f of 0. This is to be proved. It means for any epsilon r greater than 0, if we find the delta such that when mod z less than delta implies mod f z minus a 0 is less than epsilon r, then our result is okay. Okay. Then its continuity follows for the. Okay. Now, since the series, since the series sigma n z to the power n 0 to infinity will converge absolutely or converges absolutely inside the circle in mod z less than equal to r, where r for any r is strictly less than r, because this was already shown. The series is not only convergent, it converges absolutely. So, converges absolutely everywhere inside a circle. Okay. So, we take the circular disk with the radius small, which is strictly less than r. Okay. This is true. Then, so the series sigma mod n r to the power n minus 1, this n is 1 to infinity, this is nothing but 1 by r, sigma n is 1 to infinity mod n r to the power n with r greater than 0. Now, this series is convergent. So, this is convergent, converges. Okay. Let the sum be S, let the sum be is S, which is different from 0, because it is non-negative terms, okay, different from 0. Okay. Now, for 0 less than mod z less than equal to r, the difference of this mod of f z minus s, which is equal to sigma a n z to the power n, and n is 1 to infinity, and that will be equal to less than equal to mod z sigma mod n mod z to the power n minus 1 to infinity, and that is again less than equal to mod z, because mod z less than equal to r, sigma mod n r to the power n minus 1 to infinity, but this is our what, s, because this difference is total is s, sum we are taking to be s. So, this is what is equal to mod of z, or less than equal to, this part is less than equal to mod z into s. But what, this mod of z less than epsilon, if I choose this to be less than epsilon, then we can get delta to be this. So, if this is less than epsilon, then this implies that mod z is less than epsilon by s, which is nothing but delta. So, the function f is continuous at 0. Okay, this proves that, and immediately this result will give that another result, which is also the result is the two power series. Suppose that the power series sigma n z to the power n and sigma b n z to the power n 0 to infinity if have both converges for mod z less than r, where r is positive, then and have the same sum for all these z, then this series are identical, that is n is equal to b n for n 1, 2, 3 and so on. In fact, 0 also 0, 1, 2, 3 and so on. Hence, if the function f z has a power series represented with the center, this represent. Hence, the representation of the function f in the form of power series sigma n z minus z naught to the power n around the point z naught, is unique. So, that goes well with the help of this previous result, just you can find out. It means, if a function f is given, then and z naught is fixed, then we can have a unique representation of the power function in terms of the power series. So, that is interesting result, and proof follows. So, I will just skip that proof. Then there are a few results, and again I am saying in the form of theorem that differentiation of the power series, and the first result said the derived series of a power series has the same radius of convergence as the original series. It means, if the series, suppose a series is given sigma n z minus z naught to the power this n is 0 to, this is a series represented by a function f z, and this series has a radius of convergence r. Then the derived series of this means f prime z. When you take the derived series will be equal to n is 1 to infinity n a n z n minus 1, that is equal to a 1 plus 2 a 2 z and so on. This is also a power series, will have the same radius of convergence, that is r. The reason is because if we apply this ratio test for the power series 2, then what happened, the n plus 1 over n plus 1. So, n plus 1 or what is the ratio, do not go for the ratio test, just okay, n plus 1 a n plus 1 over n a n, this is our term, is it not? So, if you get for the limit of this, okay, now this is our n minus 1. So, n term will be equal to n plus 1 n plus 1, okay, and this is the n minus 1 term. So, we can say this is equal to a is a reverse way, is it not? So, we can get the derived series will be n plus, okay. So, u n plus 1 limit of this n plus 1 n n, okay, ठीक है. So, limit of this mod of this as n tends to infinity is the same as limit of this is 1. So, it is the limit of mod n plus 1 why n, why it is the n term will be n plus 1. So, it is n plus 1 and this is below, okay, it's okay. So, you will get the n minus 1 term, n minus 1, it's okay. Now, there is no problem, okay, n plus 1 and then n plus 1 and n. So, this is the same as this. So, it will be the same as n plus 1 and n because this limit is 1. So, we get this, it means this is nothing but the 1 by r. So, it is a 1 by r, it means that it will have the same drive. Similarly, for the second part, the integration, the power series integration. If we integrate the whole power series, the integrated power series that is equal to sigma n is 0 to infinity a n over n plus 1 z n plus 1. This is the integrated power series, that is a naught z a 1 by 2 z square and so on. By integrating term by term has by integrating obtained by integrating term by term the original series that is sigma n z to the power n 0 to infinity. Original series has the same radius of convergence as the original series है, as the original series, okay. So, we get this one original series, clear. Now, the reason is again simple, because if you go for the n term by divided by n term, again you will get the similar things. So, it will follow from here. Then third is, if suppose we have the two power series, say f 1 z is one power series a n z n 0 to infinity having radius of convergence r 1, another power series having radius of convergence R2 and if I add these two series Bn, sorry, this is Bn. If I take An plus Bn z to the power n 0 to infinity, then the radius of convergence of the sum of the two power series, that will be equal to power with radius of convergence R 1, it is a power series radius smaller of R 1 and R 2 has the radius of convergence of this power series will be the smaller of R 1 and R 2 will be one of them that which is smaller of R 1 and R 2. So, that is the result which we have. Okay. Then lastly, we have one theorem without proof, of course. So, that result is shows that every power series represents a function. A power series, that is analytic functions. Okay, and their derivative. A power series with a non-zero radius of convergence, with a non-zero radius of convergence, a power series with a non-zero radius of convergence R represents an analytic function at every point interior to its circle of convergence. The derivative of this function are obtained by differentiating the original series differentiating the original series term by term. All the series thus obtained have the same radius of convergence. As the original series. Hence, the first student, each of them represents an analytic function. So, this is the result which we are interested, that a power series with a non-radius of convergence R represents an analytic function at every point. And since the derived series will also be represents a power series with the same radius of convergence, so derived series will also represent a function which is analytic. Hence, all such derivatives of the function which is represented by a power series are basically analytic, and all its derivatives are also, and that is what this is. Thank you very much. Okay, thanks.